So you rely on science, right? We all do, pretty much every day. Especially for these big, complex challenges. Think about improving crops through genetics, plant breeding, that sort of thing. But how do we actually know the science is solid? How can we, trust the results we're basing decisions on?
Yeah, that question of trust
Yeah.
is absolutely fundamental and particularly critical when you're dealing with huge data sets, complex analyses. It's really the core of what we're digging into today. We've been looking at some fantastic source material.
And this isn't just any material, right? This comes straight from the transcripts and the class notes from Professor Guilherme da Silva Pereira's statistical genetics course. That's at the Federal University of Viçosa and the Department of Agronomy. So really grounded stuff.
Exactly. And our goal here, our mission, if you like,
Yeah.
is to pull out the key insights, especially around this crucial topic, reproducible research.
Okay, got it. So this course, it covers some pretty hefty topics over 15 weeks. Things like molecular markers, linkage mapping, QTL analysis.
That's right. And it sounds very hands-on, a learning by doing approach, using tools like R, RStudio, Github,
Yeah.
the works.
Tools lots of people listening probably use or are thinking about using.
Definitely. But what the course really confronts is this, well, slightly uncomfortable truth in science, which is fabricated data, results you just can't repeat, studies that aren't reproducible. It's a real problem.
Yeah, I've heard about this. It's serious enough that big journals are changing their policies.
Absolutely. Journals like Nature, for example, are now requiring much more detail on methods, sometimes even asking for the raw data itself. They want more transparency.
And I guess this gets even trickier with genetics and genomics, like in plant breeding. The data is just enormous.
Enormous, high-dimensional. And you can't just eyeball it to see if it looks right, The analysis workflows have so many steps. Checking every single calculation manually is, well, basically impossible.
Right. And unlike maybe a simple chemistry experiment where you expect a certain color change.
Exactly. With complex genomics, you often don't have a super clear expectation of the final numerical output, which makes it scarily easy for what they call silent bugs to creep in.
Silent bugs, you mean? Like
Yeah.
errors in the code that don't make it crash?
Precisely. They don't throw up an error message. They just quietly give you the wrong number.
Oh, wow.
Yeah, it might look plausible, but it's subtly wrong. And because you lack that strong prior expectation, these things can just slip right through.
Leading to potentially flawed conclusions. Okay, that's concerning.
It really highlights why reproducibility is so critical. It's the main defense against this kind of thing.
So, given all that, how does the course material suggest we actually do science more reliably?
Well, it focuses on two really linked ideas. First is robust research.
Robust research, meaning...
Building in safeguards all along the way.
Yeah.
Being careful, deliberate, trying to prevent mistakes from even happening.
Okay. And the second idea?
Is reproducible research, which we mentioned. That's about making sure someone else, or even you, later, can take your starting data and your code.
And get the exact same result. The ultimate check.
Exactly. It's about transparency and correctness. And the course lays out some key ingredients for this, like massive emphasis on documentation.
Documenting not just what you found, but how you found it. Sharing methods, code, data.
Absolutely. And adopting a certain mindset, too. There's a quote mentioned, never ever trust your tools or data.
Huh. That sounds intense, but it makes sense. Garbage in, garbage out.
Right. You have to be critical, make the data prove itself, and practically speaking, turn frequently used scripts into proper tools. Don't just copy-paste.
And collaboration helps too, right? Getting another set of eyes.
Hugely important. Maybe even paired programming, where two people work on the same code together. It catches so many things.
Okay, so that's the mindset. What about practical tips? How do you actually make your work reproducible day to day?
One big one is write code for humans. Make it readable. Add comments. Use clear, consistent names for things.
That sounds like it helps others, obviously, but also yourself down the line.
Definitely. Your future self trying to remember why you did something 6 months ago will thank you. Trust me.
I've been there. And the flip side.
Write data for computers. Format it consistently so machines can read it easily. Name files clearly. Automate repetitive tasks to avoid simple mistakes.
Simple copy-paste errors? Yeah, those can be killer. And managing changes, that seems crucial too.
Oh, absolutely critical. Make small incremental changes. Get feedback often. And use version control.
Like Git and GitHub, which the course highlights.
Exactly. Track every single change, know why something changed. And a golden rule, never ever change the original raw data directly. Always through code.
Makes sense. Keep the original pristine and use existing tools, Don't reinvent the wheel.
Please don't. Use reliable libraries and packages that are already tested and widely used. It saves time and reduces potential errors.
So the course really pushes R, Markdown, RStudio, GitHub as this kind of core toolkit for reproducible science.
That's the impression, yeah. They seem central to implementing these practices.
Okay, let's bring this back to you listening. Why should you care about all this? Being robust, reproducible, it sounds like extra effort up front.
It can feel like it initially, but honestly, it makes your own work so much easier later on. Need to rerun something, revisit an old project, reuse part of an analysis. If it's reproducible, it's straightforward. If not, well, good luck.
And it just makes you a better scientist, right? A better collaborator. People can trust your work, build on it easily.
For sure. So the takeaway from Professor Pereira's course material seems clear. Reproducibility isn't just some nice-to-have ideal. It's a practical necessity, especially in data-heavy fields like statistical genetics. It takes effort, yes, but it pays off hugely for reliable science and smoother work for everyone.
Right. So thinking about these challenges, especially those silent bugs in complex analyses, it makes you wonder, doesn't it? How many published findings out there, especially the ones based on really intricate computation, might be genuinely difficult, maybe even impossible for someone else to actually verify, something to chew on?